All right, in this video, I'm going to be proving the fundamental theorem of calculus for you. This is a thing that I think I've done for various AP calculus classes, when somebody asked for it. But today I am just going to record the video so I have it ready for the next time somebody asks. And so before I jump in, I need to remind you that the definition that we take of the definite integral is that the, pardon me, I used x instead of t over there, but the integral from a to b of f of t dt is the limit of the Riemann sums where the norm of the partition is going to 0. Specifically what that means is that, when we're going to cut up our interval into slices to run a Riemann sum on it, we need that the width of the largest subinterval is going towards 0. Yeah, that's what we call the norm of the partition. That's going to necessarily mean that n goes to infinity. Okay, so that means that n is going to infinity. It's the limit of the Riemann sums as we let our rectangles get really narrow and we take a lot of them. Okay, that's the idea. Okay, so the theorem, I'm going to pause and write it out. And the theorem says that if, we've got a differentiable function f, then the integral from a to b of f prime of x dx is given by the difference of f of b and f of a. Okay. That we can compute a definite integral by finding an antiderivative and looking at the net change in it. Okay. I mentioned that f is differentiable, which I think is pretty clear. If we're going to antidifferentiate f prime, then f prime is going to have to exist, right? Because we can't just integrate something that doesn't exist. And what else? Some people will say that, we'll write this as f and let g be an antiderivative of f. If f is continuous, then this can hold, but this will be fine. Okay, so I'm going to just say, let's take our interval a to b and let's just chop it up any old way. Okay, so maybe I'll just draw the picture. Here's a and there's b. Okay, and then I'm going to just, maybe a dot, dot, dot. Say we don't know what's happening in here, but then I'm going to, chop it up there also. All right, so I'm going to call this, hold on, let me make sure I'm going to get my indexing right. I think I'm going to start calling this x0. So this will be x0, x1, x2, x3, x4, up to xn, I believe. Let me just make sure. x0 up to xn, yes. And then I've got a and b on either side. Okay, so I've got, let's see, my 0th, 1st, 2nd, 3rd, 4th, plus 1st. Okay, I feel like I've got too many subintervals here, but let me look and make sure. I think it's going to be all right. Oh, and I see where we're going here. So, what I'm going to do is I'm going to, kind of conveniently write, start with f of b minus f of a. And then I'm going to just add some clever forms of 0. Okay? So I'm going to start with f of b minus f of a. And that's going to be equal to, start with f of b. And then I'm going to kind of add and subtract cleverly. I'm going to start by adding f of x in, okay, I understand what I did. Okay, so, pardon me, I misread my notes. And you'll see what I did is I erased a and b because I need a to be x0 and b to be xn. This makes so much more sense to me now. Okay, so f of b minus f of a is equal to f of b, which is xn, okay, minus, okay, so I'm going to start adding and subtracting backwards. So I'm going to start, minus f of x n minus 1 plus f of x n minus 1. And then I'm just going to keep adding and subtracting those same ones, or these same f of x i's, as we run all the way back down to x2 and x1. Okay, so my last couple of terms of this will be, so maybe I'll just, where if I were to group them pairwise this way, we'd be adding a bunch of zeros. Okay, so f of x n minus 2 plus, a whole bunch of other things, and then plus f of x2 minus x1, or f of x2 minus f of x1 plus f of x1 minus f of a, which was x0. Okay. All right, so this is the same thing as f of b minus f of a. I've just added in, I think, I've just added in, say, n copies of 0. All right, now I'm going to collapse this down kind of pairwise, like I'd said, into summation notation, which is going to be sum as I runs from 1 to n of f of xi minus f of xi minus 1. Yeah, here we go. And this is as I runs from 0 up to n. Is that true? No, I want 1 here. All right, and then here's where I'm going to apply the mean value theorem. And so I need to remind you that if a function is differentiable on a closed interval, well, I suppose this would be all right on the open interval, but there's going to be a place on the interior of the interval where the average rate of change, the slope between the 2 points, is the same as the instantaneous rate of change of the function. So there's a place where f prime is equal to the average rate of change. And so I kind of just put a little bubble over here, and I said on the, I to I plus first subinterval, we're going to, I'm going to actually maybe I'll just even draw the picture of it for you. Over here, there's going to be some place where the slope of the tangent is equal to the average rate of change. So what I'm going to do is I'll just say the average rate of change is going to be that blue line, and the slope of the tangent is in red, and it looks like that's going to happen somewhere around here. Oh man, that was not good. But, you see the point. Okay, and when we track that back, because f is differentiable, we know that this is going to happen. We can track that down to some x value where that happened, okay? And we're going to call that ci. And now the important thing about this, and I'm going to write out the formula, is that f prime at ci is equal to the average rate of change of f over that interval. Okay, so this is f of x I plus 1. And I'm realizing that, I'm doing I and I minus 1 and I plus 1, but I hope that you'll forgive me that and you'll see what I'm doing here. F of x I plus 1 minus f of x I divided by run. Well, x I plus 1 minus x I. All right. That's what we are guaranteeing from the mean value theorem right here. Okay. What if I were to say, well, this is kind of a lot to carry around. This is a delta x, right? The width of the subinterval. And so I'll call that delta x sub I. Then I could multiply both sides by this delta x sub I, and I could say that this, necessarily implies that f prime of ci times delta xi is equal to f of xi plus 1 minus f of xi. All right, and now I'm pretty much ready to make that substitution right here for right there. And again, I hope you'll forgive my indexing imperfection here. I'm not sure, somewhere along the way I should have been smarter. But I'm going to actually make that substitution. this thing along. And then I'm going to say that, you know, based on our definition of the limit of the Riemann sums, if we take the limit of this as, you know, the norm of the partition goes towards 0, or the number of rectangles goes towards infinity, this will become the integral from a to b of f prime of x dx, okay, by our definition. And so that's going to be the proof of the fundamental theorem that we're going to give in this class.